All right, so the last seminar of today is from Nikolay Bobev.
Thank you. Thanks a lot to the organizers for putting a birthday meeting on. I'm going to tell you about work. Oh, and thanks to all of you for hanging around so late after a full day of talks. I'm going to tell you about work I did in these papers and a couple of more to follow. It's mostly work I did with these two people who are excellent collaborators. Junho, who is in Leuven, and Val, who is in Saclay. Okay, so we're at a birthday party, so that this is the paper we're actually celebrating. But in my talk, I will also use another paper that has a birthday, which was last week. It's this one. So this is a paper in which the low energy theory on N-M2 brains was understood in terms of a Chern-Simons matter theory. Okay, and I'll call it ABGM model for obvious reasons. Okay, so what's the motivation for this work? Well, this identity Z is equal to Z is on one hand obvious, on the other hand we should work on it, I think. So that's basically the motivation for the talk. And I will be using mostly the Z on the left-hand side. So I'll try to use these amazing tools of supersymmetric localization to compute the path integral of strongly coupled CFTs, and then try to learn about the right-hand side, which is the path integral of a string or M theory. And specifically, I'm going to be interested in subleading terms in the large N expansion in the hope that we can learn something about corrections to supergravity. Why is this interesting? On one hand, we don't have too many tools to study ADS vacua in string and M theory especially. And on the other hand, such subleading terms at large N should teach us something important about the dynamics of black holes. Okay, all of these things are very broad and lofty goals. To be specific in this talk, I'm going to focus on ADS4, and thus I'm going to be specifically looking at 3D superconformal field theories. Okay? And you should feel free to interrupt me at any time if you have questions. Okay, so here's the plan. First, I'm going to tell you about this ABGM model on S3. Then I'm going to tell you about how to compute the path integral on another background, which is not S3. Then I will explain how all this has implications about holography and black holes. And finally, I will briefly mention some other N equals to 2 supersymmetric models that are cousins of ABGM, but are not exactly that. Okay, so ABGM on S3. First, I'm going to start off with a lightning overview of what the theory is. So this will be in N equals to 2 superspace. I have 4 bifundamental chiral superfields, A1, A2, B1, and B2, and they have a specific superpotential. The gauge fields are UN times UN, and there's a Chern-Simons level K and minus K. This is imposed so that you actually have a parity invariance of the model. When K is bigger than 2, you have N equals to 6 SUSY, and when it's 1 or 2, you have an enhancement to N equals 8. And this model, the claim to fame is that this should actually be the QFT that is capturing the low energy physics of N-M2 brains on C4 mod ZK. We will be interested in this in this model in the large N limit, and there's actually at least 2 interesting large N limits you can take. The first one is to keep K fixed and take N large, and then this should be corresponding to what I'm going to call an M theory limit, and the dual should be ADS4 times S7 mod ZK. So this looks like an orbifold, but it's actually a smooth action, so it's a smooth manifold. And then the map between the Sugra parameters is that L, which is the scale of ADS and S, over the 11D L Planck to the power 6 is equal up to 2s and pi's to K times N. Another thing that you can do is more like a 't Hooft limit, where you keep N over K fixed, and you call it lambda, and then you take both of them large. In this way, you would make a connection. So what happens effectively is that this ZK acts on, so you can think of this sphere as a U1 bundle over CP3, and this K acts on this U1, and if K is very large, you are effectively going to a CP3 here, so you're in the type 2A limit of the model, and here's an identification of the other dimensionless parameter, G string, in terms of L and L string. So in this way, we have access to the type 2A string using quantum field theory methods. Okay, good. So this is the superconformal field theory, and S3 is conformally flat manifold, so you can put this model on a sphere, on a Euclidean sphere, without actually breaking any additional symmetries. One reason to do this is that if you do it, you can actually use the tools of supersymmetric localization to reduce the path integral. Here I have a path integral without any sources, so just as a function of these n and k integers, you can reduce the path integral to a matrix model. So roughly speaking, you'll have to integrate over these mu and nu variables, n of them. These mu and nu are eigenvalues of the scalar fields in the vector multiplets. And then the integrand is something specific which arises from the on-shell action of the QFT and then some one-loop determinants around it. Okay, so once you have a matrix model, you should go back to the literature on matrix model and see how to analyze it at large N. And this can be done in a variety of ways. I'm just listing them here. You can use some tricks to map this matrix model to some Chern-Simons theory on S3, and this has a connection with a topological string on P1 times P1. You can do something like a brute force large N numerical analysis. There's also a map to an integrable model of a Fermi gas. So all of these models have been explored, methods have been explored soon after this paper of Kapustin, Willett, and Yakov. So anyway, here's an answer. So this answer comes from actually using this Fermi gas formulation of the model. So the path integral at large N looks like this. So it's a closed form expression for all orders in 1 over N. And this is accurate up to exponentially small terms in e to the minus square root of N. So when I say all order exact, I will mean only this first term excluding these instantons. So these e to the minus square root of N here should be in the bulk, they should be Euclidean M2 branes. M2 instantons. Here, B and C are some constants which are fixed in terms of this integer k. And there's also n, of course, here in the argument of an Airy function. So this AI is an Airy function, which is a well-known special function. And there's an annoying curly A here as a prefactor, and it has some kind of not very explicit form as an integral, or you can actually expand it at large K, and it has this kind of a nice expansion as a series at large K. Okay, so at large N and fixed K, you can expand this Airy function, and you have an answer that looks like this. So here I've given only the first few terms up to n to the power 0, but of course it's algorithmic to expand to any order that you like. So I'm going to make comments for ADS-CFT of the first 4 or 5 of these terms later on in the talk. What I want to emphasize is that now that you have this exact answer, is you can do kind of an illegal operation. So this answer was obtained by fixing k and taking n a large, but now I can re-expand by assuming that also k scales as n, and I can rewrite it as an expansion of a string theory, which should be the type 2a string. And it looks schematically like this. So I have powers of n here, and this g is the genus of the worldsheet of the string. And there's also powers of lambda up in front. And these fg's here, fg of lambda, are the free energies of the worldsheet of the string of genus 0, 1, 2, and so on and so forth. And what I want to emphasize is that they're explicitly analytically computable to any order that you want, up to exponentially suppressed in the coupling terms. So the way that you should be thinking about these free energies here are as a large lambda kind of expansion of the type 2a string on ADS4 CP3, re-summed at finite lambda up to these e to the minus square root of lambda corrections, which should be dual to worldsheet instantons. And there's an interesting shift here of lambda with -1/24, which allows you to have these compact expressions. And I want to stress that we don't know how to compute any of this from the worldsheet of the string, of the type 2a string. So this is a QFT answer that you rewrite as a worldsheet of the string theory answer. Questions about this? Okay, everyone is happy. Good. So back to large n. So as I said, you have these 3 leading terms at large n. Here n to the 3/2, n to the 1/2, and log n. And already in the early days of ADS-CFT, it was kind of confusing how you get this n to the 3/2 power if you have an underlying gauge theory of n by n matrices. So this matrix model is an answer to this, also, although not quite an explicit one. There's some intricate cancellations of eigenvalues that kill the leading n squared term, and this n to the 3/2 is the first subleading term, which is now the leading one. In the bulk, this n to the 3/2, the coefficient of n to the 3/2 is related to the volume of the internal space. In our case, the internal space, so this is a general formula valid for any internal Einstein manifold X7, and if you take this orbifold of S7 here, you'll have an exact match with the matrix model result. The subleading term, as we showed, comes from some higher derivative terms in supergravity, which I can explain, but this will mean that I'll have to give another talk. Anyway, believe me that this is also a thing we can understand from the bulk. The log n term is a bit more interesting. It's somehow is not a local term. It's not a power of n. So it actually comes from treating the kk modes on this space as quantum fields and letting them run in a loop around this background. And it was shown in this work that if you do this, you would obtain exactly this 1/4 log n. And then, as far as I know, we don't understand how to get all of these extra terms, which we know from the matrix model. We don't know how to get them from the bulk. So it's an interesting open problem for ADS-CFT. Here, I should say that, that there's at least one person in the audience who would probably disagree with this. There is some interesting work about obtaining the full Airy function using 4D ADS4 supergravity. I'm not going to say anything more about this. I think it's an interesting proposal, but I don't understand many of the details, so I would encourage you to go and look at the paper. All right. Now, everything I told you about is something that in a QFT course we call 1. So when you teach QFT and you introduce the path integral, you normally say a z without any sources is equal to 1. Well, it's not 1, it's a big array function that knows about string theory and M2 branes and so on. But it's still interesting to add some sources, and you can do that. But we should keep in mind that we also want to compute stuff. So I still want to use this tool of SUSY localization. So I want to add only the sources that are compatible with the supercharge, which allowed me to use this kind of trick. And these are very specific sources that are certain squashings of the sphere. So this parameter b here, which appears here, is a certain squashing that makes the sphere not round, but kind of an ellipsoid with u1 times b1 invariance. And these m1, m2, and m3 are certain specific masses that are called real masses that are associated with the flavor symmetries of the model. You don't need to know the details. What's interesting is that after a series of papers on this, what emerges is that the full answer with all of these insertions of the sources still appears to look like an array function. I want to emphasize that for general values of b, m1, m2, and m3, this is not an expression that has been analytically derived, but there is a substantial amount of evidence that it's true. Yeah, and these constants, b and c, which were simple numbers before, are now functions of the sources b and m1, m2, and m3. Okay? So we have a nice, complicated answer, and one may ask, what is this good for? It encodes certain integrated correlators of the theory on flat space, but it's not so easy to understand which ones exactly. For the 2-point functions, it's actually not so hard, but for the higher point functions, it kind of requires a lot of work, but it's important to do this work, as emphasized by these people, because out of these integrated correlators, when you view them at large n, they give you predictions for certain couplings of string and M theory beyond the leading supergravity approximation. I'm not going to talk about this much more, but I just want to emphasize that this answer is an important one which can be used to eventually understand string and M theory better. The simplest example is the 2-point function of the energy momentum tensor. So here's how it looks like in flat space. It's completely kinematically fixed up to one real number, CT. And I claim that you can compute this CT exactly from the answer I showed you before, simply in this way, like differentiating the free energy on the sphere, a log of z, twice with the respect to the squashing b, and then putting b to 1. Essentially, each power of b inserts one energy momentum tensor. Since b is a squashing of the sphere, it acts as a source for the metric, and it inserts a power of the energy momentum tensor. So here I've given an answer only up to order n to the 1/2, but this is calculable to any order that you want in 1/n. Okay. Any questions about the sphere and the squashings and all that? Okay. Everything is either completely clear or you're completely lost. Hopefully the first one. Yeah, so all of this was at finite k, large n. Yeah, so all of this except these expressions that were obtained in a cheating way. These ones. Everything was at finite k. But here I have this comment that these results agree with things computed with the topological string description. The issue is that these answers are very simple, and the topological string gives you much more complicated answers. The reason is that with this method, you include these e to the minus square root of lambda corrections, which are worldsheet instantons, and make these answers much more complicated.
The answer of the topological string brings some nice modular forms, right?
Yeah, I think polynomials or powers are nicer than modular forms to work with, but yes. The answer from the topological string is a modular form, but then if you want to use this to compute the genus 11 free energy, good luck. Whereas with this kind of cheating method that we did, you can go to any genus that you want, excluding worldsheet instantons. That's the price that you have to pay. Yes? Very good, very good. So this model is from the start parity even. You can do a number of things to modify it to do parity odd, and then people have done such things, and yes. I'm not aware of a full, like, ARI type answer for parity non-invariant CFT, so it's all approximations that I'm aware of off the top of my head, but in principle, yes. It can be done with this method, yes. That's a limit, yeah. People have looked at such a limit, but I don't know much about it off the top of my head. So let me not embarrass myself with making statements. Okay, so everything so far was, in some sense, smoothly connected to the conformal point, the round sphere. Now you can ask, can I use similar methods to address questions that are somehow disconnected from the round sphere? So here is what I'm going to talk about, which is an example of this, and it was already mentioned actually in Dario's talk. So I will call this the topologically twisted index because that's how the authors called it, but it's nothing other than a partition function on S1 times a Riemann surface. So I'll assume that this is a compact genus G Riemann surface. And then to keep a little bit of supersymmetry, I'll do a twist here with the U1R symmetry. I want to emphasize that I'm doing a twist here on the Riemann surface, but on S1, I still have a dynamical quantum field theory or quantum mechanics. So if you study this model, it can be shown that, again, the path integral reduces to a matrix model for any 3D n equals to 2 Lagrangian quantum field theory, as was emphasized by these people. And the answer doesn't look very pretty, okay? So for the next 2 slides, there will be scary formulas, but don't worry, you should not memorize them. I just want to show them to you. Okay, so the matrix model is kind of annoying. It's, again, a function of these n and k, which are the parameters of the theory, and you can then insert additional parameters which are associated with the flavor symmetries that I'm going to call n and delta, and they appear in the integrand here. So you still have to do many integrals, and you have to sum over certain integer gauge fluxes, and so on. It's a mess. And then SUSY imposes constraints on these parameters, which we already saw in the discussion by Dario Martelli in the morning. Okay, so how do we deal with this model? One thing that was done, which was very nice, again by the same group of people, is to do this contour integration in a specific way, and essentially use the residue theorem. So you have this collection of matrix integrals to do, and you do them one by one in a specific way, such that you'll get essentially a sum over residues. This still looks like a mess, but you don't have any integrals to do. You just have to solve algebraic equations, which are called Bethe-Ansatz equations. These equations encode the residues that you have to compute. So all that you have to know is that if you have a way to solve all of these equations, and you put the solutions back here, you have evaluated this path integral. Okay? So now we have reduced the problem from integration to algebraic equations, but it's still not an easy problem because these are annoyingly hard equations. Especially at large n, you have many, many equations to solve. So how do we do this? Actually, these authors studied the saddle point approximation of the original matrix integrals, and they found an analytic solution. The solution for these eigenvalues x and x tilde looks like this. It has a scaling with n, and then these ti and vi, so a real and imaginary part, there's some functions, which I'm not giving you here, functions of these background fields, the n and delta, the real masses and the flavor fluxes. So what did we do? So at large n, at infinite n, this is the exact analytic answer. And if you put this back into the path integral, you obtain that the path integral scales as n to the 3/2. And you compute the coefficient in front. What we did to obtain a finite n answer is we did a lot of numerics. So we have algebraic equations to solve, and we know the analytic solution of these algebraic equations at infinite n. On a computer, you cannot really do infinite n, so we did n a few hundred, and we asked the computer, find me a solution of these algebraic equations near this analytic solution. So this is our method. So with this very pedestrian method, we are able to obtain many answers at finite but large n. And out of these many, many numbers, we obtained a function. So here's our answer for this index at large n. I want to emphasize that this is an exact answer. So exact to all orders in 1 over n, excluding these e to the minus square root of n corrections. So this is really an answer that is analogous to the Airy function, except that it is not an Airy function. It's a much easier function. It has 4 terms as long as you write an answer in terms of this shifted n, which we called n hat. So I have an n hat to the 3/2 term, n to the 1/2, log n hat, and then an order 1 term, and that's all. And this is an answer as a function of all of these real masses and flavor magnetic charges. Okay? So we obtained this again, not with any analytic insights, but with just doing a lot of brute force numerics, sadly. There is a special limit of this index, which I call the universal index, which is when you turn off all of these flavor fluxes and all of these real masses. And then the answer is really, really simple. So this is the analog of this Airy function that I began with on slide 2 or maybe 3, I don't know. So this, again, is the full answer up to e to the minus square root of n. And in this case, we're actually able to get information about this order 1 term quite accurately, and it looks like this. So again, this f0 hat is the analog of this annoying curly a of k, which I showed you for the Airy function. And again, it has a very similar expansion in terms of 1 over k, some rational numbers here. Yes? Correct. So here, if you really are emotionally attached to n as a variable, you also have an infinite 1 over n expansion. But if you like n hat, then it's a finite series. And this is one of the interesting aspects of all of this, is that there is some intriguing QFT suggestion that this n hat is the natural variable. Yeah. Good questions. I don't know the precise answers, but yes, you should somehow think of this n hat as some kind of the better bulk variable instead of n. It seems, at least from these matrix model answers. And then if you want at small values of k, we can compute all of this up to, I don't know, 18 or 20 digits or something. I'm giving you very accurate answers here. And as I said, all of this is numerics, but it's very, very accurate. So you should probably believe it. We were even able to compute the coefficient here of e to the minus a square root of n, and the coefficient of in front of this e. So we have very good control over the numerics. All right, how much time do I have? 10 minutes. Good. And again, I want to emphasize that all of this can now be rearranged into a type 2 a string expansion. Now the bulk is not ADS4 CP3. I'm going to tell you what the bulk is in a minute. But again, these free energies of the string can be computed explicitly, again, in terms of this lambda minus 1 over 24. And I wish I knew. I'm not aware of a string theory. I want to say that people doing integrability on ADS4 CP3 found this lambda minus 1 over 24 appearing in their calculations, but I'm not aware of a nice explanation why exactly this renormalized lambda is the natural one. Okay, what happens in the bulk? So exactly, but that's exactly the small lambda limit where worldsheet instantons are going to come and cure it. And you can see this explicitly from the topological string, which is the full answer as a function of lambda. And then you see that these things agree up to lambda of order 1 or even 1/2, and then one answer diverges and the other one is finite. So always good. Physics works, but if you are not interested in worldsheet instantons, these are the nicer formulas. What happens in the bulk here is that now I have this twist. I have ABGM on S1 times the Riemann surface, so the M2 branes are not in flat space. So the bulk dual better not be flat space, and it is, and indeed it's not. I will treat the bulk now in a Euclidean way. So the claim is that this simple 4D metric is a solution of 4D n equals to 2 Euclidean supergravity, which keeps 2 real supercharges. So there is the Riemann surface, tau is the circle, and r is the usual ADS direction. Q looks like an electric charge. The magnetic charge is not free. It's fixed in terms of supersymmetry. In terms of the scale of this Riemann surface due to supersymmetry. Kappa is the Ricci scalar of this Riemann surface. You can compute the on-shell action for, I'm sorry. The solution is completely smooth. It looks like a cigar times a Riemann surface, as long as this G times Q is bigger than kappa. G, by the way, is 1 over the scale of ADS. And then this fixes the periodicity of this beta tau, the radius of the circle, if you wish. And then I have a smooth Euclidean background, which is asymptotic to ADS4. I can easily compute its on-shell action, and it's very, very simple. It looks like this. When the genus of the Riemann surface is bigger than 1, this metric admits a nice Lorentzian interpretation as the extremal supersymmetric Reissner-Nordstrom solution. To do that, I need to do 2 things. I have to have the genus bigger than 1, and Q has to vanish. For any other choice of genus or Q, I only have a Euclidean background without a nice Lorentzian interpretation. But this on-shell action is valid in all of these cases. And if you have a black hole, as usual, and as we heard in Juan's talk, the entropy is minus this on-shell action. Okay. So, as I said, this is in the limit where Q vanishes and G is bigger than 0. This is nothing but the extremal magnetic Reisner-Nordstrom in ADS4. Okay, so the claim is that this is the background dual to this TTI, dual to this index that I was mentioning before. It can be uplifted to 11 dimensions in this way. So this DS4 is exactly the 4D black hole. There's an internal CP3. This is the potential for the Kähler form here. And this A is the 4D Maxwell field, which uplifts as a Kaluza-Klein field. You have some internal fluxes and so on. And what we claim is that this TTI quantum field theory answer should give you the path integral of M theory on this background to all orders in 1/n. So of course, that's a very strong claim. So we better have a way to check it. So what can be done from the bulk is, again, you can compute an on-shell action. And that will give you the leading n to the 3/2 term. You can include these annoying higher derivative terms, and that will give you the subleading n to the 1/2 term on the nose. And as some people in the audience did, you can again study these one loops in 11D of the KK modes, basically, and this will give you the log n term. And again, we don't know how to do anything more than this from the bulk, but as I showed you, I have an answer for all of these dots from the QFT. So if you believe all of this, it seems like this is a prediction for the entropy of the black hole. 5 minutes. Okay, good. I want to say that I showed you the simplest black hole solution without any of these flavored fluxes or real masses, but you can actually construct much more involved black holes which have all of these parameters in them. Good. One thing I want to mention very quickly is that this is not specific to ABGM. So we looked at a bunch of other models just to understand why we found such very, very simple expressions. So all of these things, you don't need to know what they are. There's some specific 3D n equals to 2 or higher supersymmetric QFTs, which have known bulk duals. And for all of them, we computed this TTI, so the path integral on S1 times the Riemann surface. And for all of them, we obtain exactly the same kind of answers. It's a finite series, if you wish, expansion in terms of this n hat to the 3/2, n hat to the 1/2, log n hat, and then an order 1 piece, and then up to exponentially suppressed terms. So this seems to be a general feature of these holographic 3D n equals to 2 CFTs, and I wish to know why. I don't know why this happens, but it seems to always happen. And again, in all of these models, there's a corresponding black hole solution, and whatever we could check for leading and subleading terms at large n agrees with these answers. Okay, this is essentially all I had to say. Here's a short overview. I told you about some exact up to e to the minus square root of n results for the path integral of ABGM on S3 and S1 times the Riemann surface. I told you how to connect some of these answers to ADS CFT. There seems to be some exact results for something that looks like an index. So this will probably mean that we may hope to understand something exactly about these Reisner-Nordstrom black holes in ADS4. And then I told you how to, well, sketched how to obtain similar answers for other holographic CFTs. Here's an outlook. Well, you can try to do now other 3D n equals to 2 models, and we're thinking about this, things that are coming from massive 2A that do not have an M theory limit, things that are coming from type 2B string theory, and so on. It would be nice to have an analytic understanding of these very, very simple answers. So I wish I can tell you more, but at the moment I cannot. One thing that I didn't have the time to talk about is that you could ask similar questions for a partition function on S1 times S2 with a certain rotation fugacity on the S2. this is the relevant object to compute the entropy of Kerr-Newman black holes in ADS, rotating black holes. For this, the answer seems to be a bit more complicated, but we obtained some nice results, again, to all orders in 1 over n. And there's some, well, there's many open questions. Some of them I already mentioned. I wish to understand this n hat object, why the QFT suggests very strongly that there is a shifted version of n which organizes the answer in a simple way. I don't know. It would be nice to understand how to do this to all orders in 1 over g Newton, if you wish. So to do SUSY localization in the bulk somehow. It would be nice to understand how to obtain some of these worldsheet answers from the type 2a string, or maybe understand how to deal with M theory. And finally, I think there should be some kind of OSV kind of relation for ADS black holes, something that is exact to all orders. And there's only hints of that for the moment, but hopefully we will get there. Thank you very much.
Questions?
Yeah, thanks for a really nice talk. That was beautiful. Do you have examples of models at the end there where you have 2 different field theories that are describing the same M theory background? So both the ABJM and the V52 have such models if you set k equals 1.
K equals, yeah, good. So indeed, I'm not going to comment on V52 because I don't know it off the top of my head. We used one of the QFTs.
It's the Dan Jasper's,
right? Right. So we use that one, I think. But for this model, if you put, so this model is not a Chern-Simons theory. This is a pure n equals 4 Yang-Mills with NF hypers in the fundamental and 1 in the adjoint. That model, when NF is equal to 1, is dual in the Seiberg duality kind of sense, IR, dual to ABGM at k equals 1, and this answer, when you put NF equal to 1, agrees with what I showed you before. So yes, SUSY localization is not rich enough to distinguish the UV physics. It only knows about the IR CFT, which is the same.
Yeah, thanks.
Yeah.
More questions?
Do you think there's an n hat for the ST partition?
Well, I showed, yeah. Well,
finite higher derivatives in supergravity.
The n hat is the argument of the Airy function, but the Airy function is not a simple power series. So intuitively, this TTI, this S1 times the Riemann surface model, it looks a lot like a 1D theory instead of a 3D theory, because you do the twist on the Riemann surface, and that somehow erases a lot of the information about the 3D theory. And that's my intuitive answer why these answers are much simpler than the full Airy function. Whereas the model on S3 is a more involved path integral, so yeah. But I don't have a better answer than that. Yes.
Sorry, I knew I had 2 questions. I forgot the second one because I came straight from the airport today to the workshop, so I'm not quite with it. Yeah, the higher derivative corrections in 11 dimensions. So what's known about them is a complete mess. The gravitational ones are all right, but the ones involving the fluxes are an enormous mess. I mean, how does one expect all of that to magically reconfigure into this beautiful answer?
This is recorded, right? So I should, yeah, it's a complete mess is a very accurate description. So if you give me a minute, I was actually confused why so little is known. So I tried to reconstruct the history. I think in the 90s, where people were studying higher derivative terms in string and M theory, they were focusing on things built out of the Riemann tensor because they were reducing on special holonomy manifolds. They didn't have internal fluxes. And so if you're only interested in that, there's some results are known, especially in type 2B string theory. Type 2A also. M theory is a bit harder, I think. Anyway, but we're doing ADS CFT, and essentially, I think, no, all of the vacua which we know under control, ADS vacua, have internal fluxes. So then you are opening a can of worms, because essentially none of these internal flux higher derivative terms are known. Even the possible contractions are not listed. So ultimately, there should be one term at order 8 derivatives. If we have a superspace with 32 supercharges, it will be one big expression with a coefficient which we can compute, because we know one of the terms, and that will be the same by some awarded entities in 11 dimensions. But sadly, we don't have such a beast, so yeah, we don't have control. The way we handled it is via massive cheating. We went to 40 supergravity and assumed that there's some kind of an EFT expansion in 1 over n, and then used some tricks to fix the coefficients there. I can give a talk about this, but it will be a 1-hour talk. Anyway, so we didn't do any 11D higher derivative analysis, because we don't know what will be the starting point, basically. Yes, very sad.
All right, if there are no more questions, let's thank Nikolay again.